Hi everybody! In this video I would like to help you with the concept of acceleration, or how fast the velocity changes. So the first thing that we want to do is set up a coordinate system, x and y axis as usual, and let's draw the trajectory of some particle that moved on the xy plane. On this trajectory, let's choose 2 points, A and B. And at point A, I'm drawing here the vector velocity corresponding to that position and the vector velocity at B. Those vectors, we know from previous videos that they are tangent to the trajectory. The line defined by those vectors only touches the curve at that point. So since we're talking about how the velocity changes, a very important concept quantity that we need to calculate is the difference between the velocity at B and the velocity at A. That's delta V AB. That takes care of the part of the acceleration concept, which has to do with velocity change. Every time you hear the word change in physics, it's always going to mean the difference between the value of the quantity at one point and the value of the quantity at another point. So what about the part that talks about how fast? For the how fast part, we want to compare the change in the velocity with how much time it took for the particle to change its velocity that much. So that means we want to take the ratio between the change in velocity and delta t. That's the quantity that we're going to call the acceleration, but here we have to be careful here and say that this is the average acceleration, because this quantity gives us an idea of how the velocity changed in the interval between A and B, but it does not give us any specific information about how the velocity changed between A and B at any interval of time contained in AB. For example, if this was a car driving on a highway, the car might have stopped, for example, in a gas station to put on some gas between A and B, right? So the average acceleration between A and B would not give us any details about the specific motion of the car between A and B. We would not know from looking at this number whether the car accelerated constantly between A and B, or whether the car had spikes of acceleration and then points where the acceleration was zero. We don't know that because all we have is the overall change in velocity between A and B. So that's why we call this the average acceleration, and we put the little bar on top of the letter A. So graphically, if you wanted to determine what is the change in velocity, we have vector VA and vector VB, and we want to find out what is VB minus VA. So what we can do is move those vector VB so that its tail coincides with the tail of VA, and we know that the difference or the change in velocity delta VAB, since it is equal to VB minus VA, then VB is VA plus delta V. That means that in graphical terms, the vector delta V needs to have its tail to the head of VA, so that VA plus delta V gives you VB. So graphically, that's the direction in which delta V should be pointing. And on this diagram, we can say then that the direction of the average acceleration between A and B is the same, because that vector is obtained from delta V by dividing it by some scalar quantity, which is delta t. So we do know what's the direction of the average acceleration between A and B. That vector is telling us overall in what direction the velocity changed when the car was going from A to B. But what if we wanted to find the acceleration at one point? How would we do that? Well, we encountered this question before when we talked about finding the instantaneous velocity after we define what average velocity means. So we're going to follow the same procedure, and that would be to take 2 points on both sides of the point of interest, calculate the average acceleration between those 2 points, and then take the limit when the difference in time between those 2 points goes to 0. That's what we want to do here. So the instantaneous acceleration is going to be defined as the limit when delta t goes to 0 of delta v over delta t. This can be written as dv dt. This is the instantaneous acceleration. If we want to find the components of the instantaneous acceleration, we can start by writing down the components of the velocity, which has x and y components, and taking the derivative of those components. So the derivative applies to the vx term and the vy. So we end up with two components, where the x component of the acceleration, it's going to be given by dvx dt, and the y component of the acceleration is going to be given by dvy dt. Since the velocity is itself a function of position, then we can write that the acceleration is the derivative with respect to time of dx dt, which can be written as second derivative of the position with respect to time. The same is true for the y component of the acceleration, which turns out to be the second derivative of the position along the y-axis of the particle, second derivative with respect to time. So these are the components of the instantaneous acceleration of a particle. And note that each component in these equations is independent of the others. Wherever there's an equation with x, y doesn't show up in the equation for the y components, or y component of the acceleration or velocity. The x component doesn't show up. So that means that, for example, acceleration in the x direction does not care about what happens in the y direction. Just because an object is accelerating in the x direction, that tells you nothing about the acceleration of the object in the y direction. This is something that is important to keep in mind. Now let's look at a specific case, which is the case of uniformly accelerated motion in 2 dimensions. So what we're talking about here is motion in 2 dimensions characterized by a constant acceleration vector. So your vector acceleration has two components, the x and the y, and the x is constant and the y is also constant. They don't have to be the same constant. So the question is, if we know that the motion of the object is with constant acceleration in 2 dimensions, how do we figure out the position along the x-axis as a function of time and the position along the y-axis as a function of time? How do we go about finding these functions? We want to find out the trajectory of the object, just knowing that the acceleration is constant. So let's start with the x coordinate. We know that the acceleration is constant, and it is equal to dv x dt. So from that, we know that the velocity, the x component of the velocity as a function of time is a straight line. And if you wanted to find how much is the slope, that means the acceleration in the x direction, you can just take 2 points, any 2 points on that straight line, calculate the delta v divided by the delta t, the difference in time between those 2 points, and that will give you the acceleration. From that equation, that is valid for any 2 points on that straight line, you get the equation that the x component of the velocity at some final instant of time minus the x component of the velocity at some initial instant of time is equal to the acceleration in the x direction times delta t, the time difference between the initial and the final positions. So this equation basically tells us how the velocity of the object is going to change with time. Now from the equation for the x component of the velocity, how it changes with time, we know that the velocity is going to change in a linear fashion, and between 2 points, some t initial and some t final, we are interested in finding what is the displacement of the object in the x direction. We know that the area under the plot of velocity versus time is the displacement. So knowing the equation for the velocity as a function of time, we can also find out what is the equation for the position of the object as a function of time. We have done this before when we did one-dimensional motion, and you might remember that the answer is that the equation that describes the position of the object when there is constant acceleration, uniformly accelerated motion, is quadratic in time. And there is a third equation that you can use for uniformly accelerated motion, which is the one that tells you the velocities, that involves velocity and does not involve time. So those are the three basic equations that you can use to solve any one-dimensional kinematics problem with constant acceleration. Now for the y component in the two-dimensional problem, if the y acceleration component of the acceleration is constant, then we have basically the same set of equations. Instead of x, we write y. So each one of these sets of equations is a one-dimensional kinematics problem. One-dimensional kinematics problem for the x and one-dimensional kinematics problem for the y components. So what we're saying then is that solving one two-dimensional kinematics problem is equivalent to solving two one-dimensional kinematics problems. One problem for the x component, one problem for the y component. Note here that if you have a uniformly accelerated motion in two dimensions, you can rotate the axis to simplify your problem. This is how you can do it. If your acceleration is constant, is a constant vector that points in some specific direction, and you choose your axis as x and y, as in the picture here, then you will see that the acceleration has an x component that is not zero and a y component that is also different from zero. So that means you are solving two uniformly accelerated motions for each one of the components. But what if you actually tilted the axis so that the x-axis coincides with the direction of the acceleration? It could be the y-axis if you want it. But if one of the axes is perpendicular to the acceleration, as in this case y prime, then ax is different from 0, but ay is 0. So that simplifies your problem considerably, because now only one of the coordinates is uniformly accelerated motion, which has three equations that you can use to solve it, whereas the other coordinate, here the y prime coordinate, has 0 acceleration, which gives you constant velocity motion along that direction, which is much simpler to solve.